previous talk we talked about introduction to kinetics and rates, and now we're going to focus on the idea of the rate law. We looked at the behavior of rates and the relationship between rates and stoichiometry, and now we're going to talk about rate laws. And rate laws, just to help calibrate yourself, have very little to do with stoichiometry. The rate law is often independent of the stoichiometry that's shown. What's actually, the rate law is a direct manifestation of what's going on at the molecular level. And so what that means is that what's going on at the molecular level doesn't necessarily coincide with the stoichiometry we see in the balanced chemical reaction. And that's something to keep in mind. It's very important to keep in mind. The particular aspect of the rate law that we're going to focus on is the rate constant and the order of the reaction, and using these bits of information. And the way we're going to do that is with the initial rate method. It's the primary way we're going to do that. So what is the rate? What is a rate law? I've been able to talk about this in a number of cases. It's that change in concentration of whatever we're going to look at as a function of time. And it turns out that we can express this rate law at any given point. We looked at a particular instant. But it turns out that that rate is always a function of the concentration for A going to B. The change in A as a function of time turns out to be equal to some constant times the concentration of A raised to some power, which we call the order. And this little k here, this is a small k, is the rate constant. Every reaction can potentially have a different form of the rate law. Just because it's in the stoichiometry doesn't mean it shows up in the rate law. What do we mean by this? For certain reactions, the rate will equal, if we had A plus 2B plus C going to D, the rate could look like K A squared. And that would be the rate law. In other cases, the rate might look like K, B, C, and A wouldn't play a role in the chemical reaction rate. Right? Regardless of what form the rate law is, again, the rate law has to be experimentally determined. Once we have that rate law, it allows us to relate the effective concentration on the rate. And this is where the idea of order comes in. The order is how sensitive the rate is to changes in concentration. Let's take a look. So here we have an example of a rate law and the orders. These are experimentally determined. You can't go to the stoichiometry and look at it and just place in stoichiometric coefficient. It doesn't work like that. We have to determine the order by observing the effective concentration on the rate. So here in this example, we have the rate is equal to K times the order, times the concentration of NO2 raised to the second power times the concentration of oxygen. Now, what this means is we can describe this reaction in a number of different ways. We can talk about the order with respect to each of the components. So in this case, we would say that with respect to NO, this is a second order reaction. With respect to O2, this is a first order reaction. There's another order that's not shown here, and that's a zeroth order, which says that certain components are not influencing. A zeroth order reaction, again, these are directly derived from the exponent, first order. Again, usually when we show an exponent of 1, it's implied, it's not observed. And an exponent of 0 is equal to 1, and so mathematically it doesn't show up in the rate law. What this means from a practical standpoint is that when you change the concentration of NO, for every time you double the concentration, the speed of the reaction, the rate of the reaction, quadruples. So you double NO and it goes up by a factor of 4. But if you double the oxygen, the rate of reaction only goes up by a factor of 2. Right? So it's a 1-to-1 relationship, whereas with a second order reaction, it is a power law. So you double it, you triple it, it would go up by a factor of 9. Factor of 9. Right? So, whereas if you change a 0th order reaction, it has no effect. You double the concentration of a 0th order component, and this would have no change. It would still be the same rate. So the order deals with the relationship between concentration and rate. We can also discuss the overall order. The overall order of this reaction, the overall order is the sum of the orders. So this would be a third order reaction. Usually, though, we're most concerned with the individual orders of each component as opposed to the overall order. All right, so let's take a look at an example. H2 plus 2 ICl progresses to form 2HCl plus I2. And we're told that this reaction is first order with respect to H2 and first order with respect to ICl. Right. Write the rate law. Write the rate law for the reaction. Well, the rate law would equal rate would be equal to the rate constant times hydrogen raised to the first power times ICl raised to the first power. That's it. That's a simple. Notice, even though this is stoichiometrically related, it requires 2 ICl for every 1 H2, it has no effect on the rate law itself. Another problem using this same rate law is, this is a very typical problem. If the rate of the reaction was 5.2 times 10 to the minus 5th molar per second, when H2 is equal to 1 molar and 0, what would be the concentration when you change these? Once we have the rate law and the rate, we can use that to figure out K. Right. Once we know the rate constant and the rate law, we can predict the rate at any concentration. So, the first step in this is recognizing that with these bits of information and the rate, we can figure out what the rate constant is just by plugging in. So good time to hit pause. So 5.2 times 10 to the minus 5th molar per second, that will equal K times the concentration of H2 times the concentration of ICl, which in this case would be equal to 5.2 times 10 to the minus 5th molar per second is equal to K. This is equal to 0.1 molar and this is ICl is 0.2 molar. Now we rearrange and solve. You get K is equal to 2.6 times 10 to the minus third. And now we come into a little bit of unit issues. All right, if you actually do the math, the units should turn out to be molar minus 1, seconds minus 1 in this example. Now, the units for K will vary depending on the order of the reaction, and that has to do with the way the units cancel. In this case, just to illustrate it, we have units. When we rearrange, just looking at the units, it's molar per second divided by molarity. Divided by molarity, these units cancel, leaving us inverse seconds, inverse molarity as our units for K. All right. So traditionally, we actually leave out the units for K. You don't actually see them in many cases because it's assumed that you already know the rate law and the units would be appropriate. But watch your units in this case, and units can actually give us a clue as to what's going on with the orders. So once we have that, we can then just plug in and solve that the rate would be equal to the rate constant, 2.6 times 10 to the minus third, molar to the minus 1, second to the minus 1, times 0.5 molar times 0.3 molar for the iodine, ICl, to give us a rate of 3.9 times 10 to the minus fourth molar per second. And the units work out, right? So the units work out. So this would be the new rate. Now, okay, let's ask ourselves, does it make sense? Does this number, how does this number compare to our original rate? How does it compare to this one? Well, we see that this rate is actually higher than the 5.2 times 10 to the minus fifth is lower than 3.9 times 10 to the minus fourth, which makes sense. We've increased the concentration. As the concentration goes up, the rate should go up. And we've increased both of them, it should both go up. So it makes sense. What this means is that knowing the rate constant and the rate law, given any concentration, we can solve for the rate. In the next talk, we're going to look at how to figure out what the order is for a given chemical reaction experimentally.